Good afternoon, everyone. I am Catherine Brookman, Associate Director, Knowledge Transfer and Exchange, and on behalf of Dr. Jack Callahan, Director of the Center of Research Expertise for the Prevention of Musculoskeletal Disorders, or CRE-MSD as we are more commonly known, we'd like to thank you for joining us today for this free webinar. We are grateful to the Ministry of Labor, Training and Skills Development for our funding, which supports the delivery of these webinars, and of course to our presenters who provide their expertise. We ask that you keep yourself muted for the duration of the webinar as a courtesy to the presenters and all participants. During the question and answer period, we ask that you type your questions into the chat box. The chat box can be pulled up on your screen by selecting the chat icon in the control panel that appears near the bottom of your screen. I will relay these questions to the presenters or a similar question should we have duplicate themes. Should you have a pressing question or issue, such as a technology glitch that cannot wait until the end of the presentation, please type this into the chat box and we will do our best to address it right away. The format of today's webinar is as follows. The presentation will be given, after which time we will have 10 to 15 minutes for a question and answer period with our presenters. This webinar will be recorded, with the recording being made available to you on our website, along with the presenter slides shortly after today's webinar. After the webinar, you will be sent a link to an evaluation. Please fill this evaluation out as it will assist us in the future delivery of our webinars. Thank you so much for joining us today. And remember to watch the CRE-MSD website and the MSD prevention website for new resources and events. Now it is my pleasure to introduce and to say a few words about our presenters. Seth Burt, our first presenter, is a health and safety specialist with Toyota Motor Manufacturing Canada. He has practiced ergonomics and safety in various industries such as energy generation, distribution, municipality, and automotive supplier manufacturing. Currently, Seth works as a health and safety professional at the Toyota Motor Manufacturing Canada, Inc. He develops and supports safety ergonomic tools, standards, and procedures for the use at the local and North American facilities. Our second presenter, Clark Dickerson, is a professor and Canada Research Chair of Shoulder Mechanics in the Department of Kinesiology and Health Sciences at the University of Waterloo. His research focuses on identifying, quantifying, and reducing work-related risk to shoulder health. Clark is also CRE-MSD's Associate Director, Research. Now, I hand this over to Seth. Seth, over to you.
Apologize for that. Thank you. So as we've spoken, we'll be presenting today on exoskeletons and give both our takes, as well as the combined research that is on its way. So just a little bit of an overview of what we're going to be tackling today. I'll give a brief introduction, as well as some gap analysis in terms of why we're going down this road of exoskeletons. Give a bit of a history on TMC's involvement with exoskeletons. Work through a bit of a plan, do, check, act around the development of an exoskeleton standard and use. I'll pass it on to Clark to talk more about UW and the exoskeleton evaluations there and around the shoulder, as well as give some next steps in future collaborations. So this is a brief introduction that's already been said. I am a specialist here at TMC out of Cambridge. I've also worked in Woodstock. I have a bachelor's degree in kinesiology and specialize in ergonomics at Waterloo, and I'm a Canadian certified professional ergonomist as well. And the pictures on to the right just to show that from the very start, it seems like Ironman is have been a general theme, and it's just an interesting passion that's been developed over the years. For TMC's sake, we do build currently 2 models, with one on its way, the Toyota RAV4 Lexus RX, and very soon the Lexus NX. We have 3 plants in 2 locations in Cambridge and Woodstock, and well over 10,000 employees, which we call team members. So to start and to understand and breaking down this problem that in which we got into, we use this hierarchic accident triangle to demonstrate the need in our area to conduct a gap analysis of our overall needs for TMC. When doing our general ergonomic assessments, we did see the concentration of issues and concerns surrounding the shoulder. And if applied that unsafe condition upwards, we do see a follow through on those risks turning into injuries down the line. Particularly cumulative MSDs are our top concern. Out of the shops, in a variety of shops, we manufacture cars here, our paint, body, weld, and then assembly. Assembly is our number one, and the resulting body part from there is more concentrated around the shoulder and upper body. So our top wide, site-wide need is on the cumulative MSD of the shoulder in assembly. And so that's what sort of started most of this work. As far as the gap analysis continued, going through the hierarchical controls, we did start to categorize with support from our local contractor ergonomics team known as Options Incorporated, pulling data for us to viewpoint our top concerns. Overhead work was noted as a concern that we've had over the years. And so for that point of view, we want to make sure we go through something called the hierarchy controls to really ensure that we've measured and evaluated any sort of control towards that risk that would prevent the injuries down the line. So by using this hierarchy controls, we were able to see, is there possibilities in automation? Is there possibilities in changing the scope of work, i.e. converting the overhead carrier to one that would be where a worker could work in front, along with adjustable platforms, hoists. All of these controls, some of them are in place, some of them are not. But in any case, the weighting around cost and implementation space far exceed the capabilities at this present time, and even technology on certain automation isn't quite there yet. We do have other controls here that would mitigate the risk around and reduce the exposure. An example of this would be something like job rotation to minimize the burden of being in these underbody overhead tasks for long periods of time. But our last line of defense here is around PPE, which is where we never had one before, but exoskeletons as being emerging technology really support with that. So what the exoskeleton does for the upper body in this particular case is to support the arms for them to allow them to work in prolonged overhead tasks. And so as demonstrated to depiction on the left. So moving on. There we go. So a bit of a timeline to TMC's exoskeleton roadmap here. We really started early on in 2017 when we were first introduced. There's quite a few models introduced around that time, and exobionics, chairless chair, and levitates airframe being a few. We started initial testing, and then it led to more of a mass trial collection period. During this mass trial, we were able to try many different type of ways of measuring the exoskeleton's impact to our team members, including subjective information from the team members, as well as some objective information through the use of EMG, wireless electro EMG readings on the shop floor. And we conducted a mass trial of 24 exoskeletons with 24 team members. And it fed a lot of the information going forward. After that period, there was some time of reflection to understand and to really understand that there's a real impact to this technology going forward. So we went to work to develop a standard that would allow us to utilize this technology and further test it. Later on in 2018, we launched our first mandated exoskeleton process within our weld shop in our Woodstock plant. And we got a bit of fame there through Wall Street and other organizations being the first to mandate exoskeleton use in the workplace as a legitimate PPE device. And then from that point, we then did a launch in our assembly shop, along with a launch in a similar mirrored weld shop. From there, we did more of extensive, more mass trialing for implementation purposes. And we gained a lot of reflection through this in our assembly shop, and took us to a point of reflecting on the differences between the processes that we've been evaluating on, and eventually led to us having more discussions, early discussions with Waterloo, and developing a more further need and protocol around testing these devices. So to back it up a bit to our practices here at Toyota, we have something called the Toyota Way, which is supported by two main pillars of continuous improvement, otherwise known here as Kaizen, and respect for people. I think this really defines not only the Toyota's mission as a corporation, but it really defines well of our ideals in ergonomic practices, both being a area of innovation, but also an area of improving the quality of life for our team members. And so this whole PDA cycle has really been sort of the foundation for us to establish more into how do we then sort of organize this innovation going forward. And so our group here in TMC, along partnered with the North American Toyota team, with affiliates from Indiana, Kentucky, Texas, and all across North America, came together and created the first exoskeleton standard for industrial use. So part of the standard is establishing things like role responsibilities, training requirements, storage requirements, fit testing, issuance, and a bunch of other forms that we can sort of understand and maintain and use this type of equipment, as well as testing and how this information can be used to fuel and improve upon what we've learned before. So one part of this plan is to really evaluate and understand what's the need, and from the process and team member perspective, how do we evaluate the objective need towards exoskeletons? So we went to work to try and define that. And one starting point was the fact that we have, thousands of processes here at any given time. We need a way to filter that number down. So we created a selection tool, which I'll go through more detail. And the next step from there is, once we filter it down, to evaluate if there's any other controls that be feasible for use. And then from there, the exoskeleton usage, we want to make sure it doesn't pose any additional harm to the team member through a safety risk assessment. So to talk a little further into those points, because it did take quite a bit of time to dive into this and figure this part out. But we do have an internal tool here that evaluates ergonomic burn called the TIBA, ergonomic burn analysis. It measures things like cycle time, otherwise known as takt time for us, duration, and posture codes. And so the question that we had was, is there a way for us to evaluate the need on just those type of metrics, as mostly the equipment that we're evaluating from an exoskeleton point of view was to improve this type of work, i.e. work overhead for a long period of time. So how do we map that out? Based on the studies through Iowa State and the EMG work there, and partnered locally here and along with Levitate, we were able to identify using something called the HCIH fatigue curve, and to sort of generalize what we're finding as the top need. So from that, we were able to sort of collaborate on that work with Jason Gillette and Terry Butler, and actually identify some sort of working tool for us to narrow down the scope of practice around this type of exoskeleton technology. So that created into the upper body postural exoskeleton screening tool, which was a good breakthrough for us to sort of narrow down the scope based on duration of shoulder, and gives us a bit of more of a direction to point towards to screen out and to take note on our highest need. But that's just the start. Really, the more important part here is that once we get down to the processes and the tasks that we want to evaluate the use on, taking account and partnering with our engineering teams and those that work on the floor to ensure that we do exhaust any other type of control. And so this generally comes down to evaluating things like space, cost, productivity, and other sort of measurables that we have here that we have to consider when launching something like this. But again, most of the cases we were able to eliminate through other needs. But in cases where the technology of, automation wasn't there, this is where exoskeleton became more of a thing for us to try and see whether or not we can make it work for us. And then the last one is to ensure that we have some sort of safety risk assessment. So it's not just enough to say that this is the last resort, we have to throw it on. We have to really evaluate whether or not there's some adverse effects. So some adverse effects, for example, for some of the equipment we've seen is things like striking impact or abrasions or entanglement when using it, because it is worn similar to a backpack. So there's very similar aspects to risk for this. And then other smaller kind of shop level management things that we've worked out. Not every process here requires an exoskeleton or needs an exoskeleton. In some cases, it can be dangerous to have an exoskeleton on in some of our processes. So we did need to make sure that it's very clear which ones need it and which ones don't. So there's no confusion there in terms of wearing it when you shouldn't be without being properly evaluated. So signage, storage, keeping it clean, 5S is important for us as it is to many other organizations. Training, so we do have some training material that we provided, and this is an example of another way of kind of maintaining the equipment. So having some sort of equipment check sheet in which our organization, our shop floor, to properly check and maintain the equipment as it's being used and change out if there's any sort of damages to make sure that it's working correctly. And then because it is in some areas a PPE and designated as such, we do have compliance to that because it is there for the team member's protection against the particular hazard it's protecting. So auditing compliance as well as understanding if there's any sort of safety concerns with using it. So we do provide, again, training for each use, and as well as providing more training embedded into their work instructions. Another part of the plan is to address the team members' concerns. So two big questions that came out of this is one is how does one address fit concerns? So for this one, I won't read every bullet point here, but just to give you some example, when we do use exoskeletons, it's generally paired with some sort of survey, some sort of way of collecting the team members' information and noting what their concerns are. We do have daily checks with the team members at any point for any work that they're doing here. To follow up on their concerns. When it comes to using their concerns, one particular notable one is when reviewing one of the exoskeletons, we noticed that some of the strapping was very rigid and small. And so there was some innovation working with that company to level up their straps and to make it more comfortable. So there is sort of a paired work with the developers themselves that takes place that we can provide some insight to improve their product for our team members' benefit. The other one is, will one develop other direct or indirect injuries and problems while wearing an exoskeleton? I don't think this will ever be completely solved. It will be something that we'll have to keep monitoring. This will be a very long-term study, but short-term wise, we have done some evaluation, conducting some strength evaluations before and after use to make sure there's no sort of changes in that sort of area. The other areas we'll continue to monitor as we go and develop some sort of surveillance program for our team members. So then we start to sort of create an action plan around these items to ensure that we do check them off. So it became into 3 stages: pre-implementation, implementation, post-implementation. So some of the things we've done is create a training package. We've created some surveys around how do we collect this information. And then I think more importantly is having more of a round table of sorts of collecting everybody's ideas and having a way to manage through the problems that have come up through use and get everybody engaged with this activity from the ground up to have complete buy-in into it. So that's been very, very helpful for us to have that engagement. So for a check, so now we're getting into a bit more of the results of what we've seen so far in terms of use. We've done really 2 main trials in the area of high need for us, which is the assembly shop. I'll talk to Weld a bit later on. But in terms of our trial comparison, in 2017 versus 2019, we did evaluate the same shop, but there was a model change between a sedan and an SUV from Corolla to RAV. So the results seem to vary based on some of that information. We did a 2-month trial versus a 4-month trial. We did one with 24 users versus 72. The number of processes or jobs went down, so it was a lot more concentrated numbers. The study design even changed as we learned more about these units. So trialing use versus non-use versus in 2019 when we attempted to do a full mass implementation of the devices, we were very much evaluating exoskeleton use over time. So from the very start of building the RAV onwards, we really did a sort of comparison of month over month, what were the changes that took place. As far as subjective information goes, it's been pretty consistent. We did recently introduce in 2019 NASA TLX as a more preferred option for us to collect sort of the holistic demands, and I'll go into more detail later on that. We've done some objective measurements. It's been very limited based on the tools that we have available, but measuring things like injury and discomfort rate, strength conditioning testing, ENG, and energy expenditure have all been part of it, some capacity. And then also realizing that there is a big difference in these trials between having 100% build, as in going at building the vehicle at a 100% rate versus a ramp up to building the RAV. When we introduced the RAV in our North plant, there was a much difference in those 2 trial comparisons. That's not advancing right now. There we go. So as far as subjective trial measurables, something when reviewing each of these measurables, because it was important for us to understand how we collect the responses from the team members' point of view. When it comes to informal feedback, there's always ways for the team members to give their voice. When looking at sort of the general comments around these devices, generally it was a big of a mix between positive and negative comments around the use of it. It continues to range, but it started out as more concerns around fit, the concerns around how the equipment, fits to their proportions. But as we improved on the fit side, we found that it actually more concentration around how well does this equipment match my environment. So that became sort of a stepping point for us. We saw a bit of a change between how we use something like RPE to NASA TLX. So RPE is more about just holistic physical demand. And we did see some initial good positive response out of using this as a way of measuring pre and post. And there's some good work done in that area. So let me skip down to NASA TLX for that sake. But when we evaluate sort of the holistic approach by taking NASA TLX, which if you understand NASA TLX, there's 6 different measurables there. We start to see one that's really started to highlight or stand out to us, which is that temporal demand and use. It seems like there's some concerns around how well I can keep up to my process based on the movement of the equipment. Equipment functional score was one that we created, but it's been very useful for us here, where it's 1 is interfered with the job versus 5 is very helpful in the Likert scale approach. So it allows us to engage with whether or not we are on the right track from, with the teamer's perspective on the, what has been, if it's been very useful for them in the process, which is ultimately what we're trying to go for. Some notable concerns so we initially had very positive response for that, but it recently changed with the different processes that we've been evaluating, with workflow pace and design as being the top concern for us. As well, discomfort, initially it was pretty positive, but recently as time goes on with evaluating this, we've seen some increase in discomfort with use. But at that time too, it was also the period of ramping up to a higher rate of production. So we'll have to come back to this a little more and understand from a discomfort point of view if anything sort of plateaus or if it continues to raise concerns. And then from an objective point of view, we had some really interesting ones here. So injury and discomfort rate when evaluating the same period pre and post, we saw a positive influence with exoskeleton intervention. Not as much as we did from one model to the other, and I'll get into more detail of why we think that could be. But in any case, it seems like there's some visible benefit to this. When it comes to the strength testing conditioning, so as I alluded to, sort of using MVIC tests to measure isolated muscle groups before and after use, we did see no evidence of strength conditioning loss during exoskeleton intervention. It's not treated like a cast. You're still very active when using it. It's not as much as a constriction in that way. And then EMG has been a great one, thanks to the support from Iowa State University to sort of kick things off for us and see it in that lens, to look at muscle groups and the fatigue effects of overhead work. The notable thing of this is that we did see 8 of 9 processes initially when we did this study see a decrease in activation, which was a positive sign for us. But it's also easy to note that these are measuring larger muscle groups, and so there's some limitations there, but it's been so far it gives us sort of a good reflection on that these devices have some sort of meaning and is working in some capacity. When it comes to energy expenditure, we're just very recently tapping into that area through a technology, through a wearable sensor. We're able to collect some information that can lead to a predictive VO2 and metabolic rate. And from that metabolic collection, we're able to compare to, say, like the NIAS thresholds and to evaluate. The thing that's interesting about the energy expenditure approach is to see whether or not on a holistic scale, is there sort of a difference? And we didn't really see much change between use and non-use from that sort of whole body holistic point of view. But it is still fairly early for us, and we need more data to make any sort of claim around that. So originally we thought, this could be us taking this objective mission and improving the design of the equipment and taking the objective information and improving our process. But it's been a sort of a mix in terms of how we approach some of this information and improve where we go from there. I mentioned the straps, but how we end up sort of selecting our process has changed over the years, and around how do we pick the right jobs for this kind of technology, or if there's another way. And so it's kind of led to some other ways of comparing our success and challenges. So for example here, weld, I've talked very briefly on weld because most of our attention has been in our assembly shop being the highest need. Our weld shop has actually been wearing exoskeletons, mandated exoskeletons for about 2.5 years now in our one of our underbody processes in weld, actually 2 of them. So looking at the differences between weld and assembly, what's working in weld and what's not working in assembly, we see some notable factors here. We see that the different tasks in assembly versus weld is much higher. The cycle time is much longer in the weld period versus assembly, which means that there's a little more time between tasks, but also the time spent in one overhead rep position for weld is around 120 seconds versus for assembly it's about 8 seconds. So very high reps, or for weld's sake it's more high duration. So if I could just show you a quick kind of slide. So this is our weld process. It's very sort of static controlled movements, but again, these are processes that have been using exoskeleton technology for quite a few years now. And this is so quite a few number of reps, quite fast movements, a lot of twisting and turning, and just a lot of repetition in general when used. And this is also to demonstrate that there's other exoskeletons out there that we're exploring and reviewing as we go. But for the most part, there's a very similar story being told here, regardless of type of exoskeleton. So this is a sort of summed up comparison that we're starting to work towards, which is dynamic versus static. When we compare weld versus our assembly processes, we see that there's a lot of potential in weld continuing on, and the comparison chart to your right there just shows a bit of a plot point. In no way is this statistical evidence or anything. It's just more or less what we're seeing and we're putting down on paper. When it comes to EFS, we're talking about 1 being interfered versus 5 being very helpful. So in that case here, those that are in this area are ones that team members are very engaged with versus those that are down here. And the average number of reps. So what was interesting to us when we plot this out, we were talking about how well it seemed like Corolla was doing for exoskeleton usage in assembly until it turned to RAV. We did see, plotting this out, that the lower number of reps per minute, i.e. the higher number of duration in some regards, that's not completely the case, but we did see that there is a better use, and mostly because of the sort of upward pressure that this exoskeleton provides. If you think of it as some sort of pushing force upwards, that you're working against it if you have to drop your arms down continuously, at the very least. So it's something that we're really interested in exploring more of. And so that became more of for us as a call for research, and this is where we're currently at. When mapping out the concerns and where our needs are now in terms of defining this, if this exoskeleton technology really is sort of our attempts to correct that overhead work problem that we're trying to solve. And this is data across 5 plants in North America. We do have dynamic work as number 1. Other concerns like bending and cabin work, space restrictions, and height of reach, those are all present. But for the most part, we need to tackle this sort of dynamic work aspect. And part of this dynamic work aspect to figure this part out is not only to improve our selection tool, but it's maybe also, opening the door to defining our processes with exoskeletons in mind now. Instead of hoping that this technology would just seamlessly integrate into our current design, it may be about manufacturing our processes a little differently with them in mind, if this is truly the control that we have to really evaluate and use. But for that, we'll need more research and to really understand the true benefits and limitations to that. And so from that, I'll pass that off to Clark.
Okay, thank you, Seth. Hopefully you're able to hear me. So I'll try not to stay on this slide too long, so you don't have to view my picture for an extended period. But the background here is to let you know that I've had this experience with shoulder research, biomechanics research, going back till my early days of mechanical engineering at Alfred University, if you look on the left side of that. And moving on, only want to highlight a couple things to you. In 2016, I did become the Associate Director of Research for CRE-MSD. And then in 2021, which is where we are now, I've been initiating this project with Toyota. On the bottom right are the various funding sources that have enabled research over the years. So I have four main goals here in the time that I have with you. The first one is this brief introduction of myself. We'll get a little bit more on the work going on at Waterloo, introduce CRE-MSD briefly, and talk about the basic science behind our approach to working with Toyota on this project, and then describe some overview details of that collaboration. So next slide, please, Seth. So CRE-MSD, for many of you are probably already familiar with it, but it is a center of research expertise for the prevention of musculoskeletal disorders. And there are two goals of CRE-MSD, or two main goals. And I think you'll see that they dovetail quite well with this project. So the first is to support workplace partnered stakeholder focused research into the primary prevention of MSDs. And the second one is to generate transferable knowledge on primary prevention of MSDs at work. So both of these are exactly right in the main line of what this collaboration is attempting to do. There is another major activity of CRE-MSD, which I would like to make you aware of if you're not already familiar, and that is the MSD Prevention Guideline for Ontario. This provides a lot of background and solutions for approaching different musculoskeletal disorder concerns across sectors. So next slide. A little more about what I'm doing at Waterloo. I do also direct a laboratory. We call it DIESEL for short, which stands for Digital Industrial Ergonomics and Shoulder Evaluation Laboratory. There are four main areas, two of which are probably most relevant to what I'll be talking about today, and those are the fundamental and ergonomics sections of that wheel. And really the fundamental knowledge needs to inform any kind of ergonomic intervention or assessment, and I hope I can make that case for you over the next few slides. And you may recognize also from several of these circles, figures, digital human models. So there is an element of that and connection to that I'll describe very briefly. So next slide. So I do teach a course on upper extremity disorders, not only occupational, but primarily. And I'm going to condense what usually takes 2 weeks into about 2 or 3 slides. So very briefly, the shoulder is considered a complex, not a joint. Often it is simplified to a joint in practical applications. But if we look at the picture on the right, it's a classic skeletal picture. There are really 4 main components or bones that we need to consider when thinking about arm movement and shoulder movement. This includes, so we have the 4 bones. There are many muscles. depends on exactly what you consider a muscle, but anywhere from 38 to over 50 by different representations. Ligaments, tendons attached to those, ligaments around the joints and tendons attached to the muscles. And as a result, there's a high level of complexity. With this high level of complexity, there are many components, and they can and do fail for various reasons that are fairly nuanced and not necessarily obvious from, say, a visual observation of someone moving. So next slide. Thanks. Two main characteristics of the shoulder are that it is extremely mobile. There are 3.5 joints that move together. There's a concept called the shoulder rhythm where there's coordinated bony movement. I'll have a visual of that in a second. But the main idea is that the complexity and the mobility allows us to put our hands in many different places in space. The ones of most concern relative to today are overhead placements, but we could not have the function that we have or the ability to do various tasks if we did not have complex shoulder movement. Along the sort of the price for that, or the trade-off, compromise it's often called, is that there's an inherent instability associated with the shoulder, primarily in one of the joints, which is the joint between the arm and the scapular or shoulder blade. And this makes it very sensitive to perturbations or loads or changes in load. In order to have this high mobility, the joint has to be very free to move. And that's usually quite positive because it allows us to get our hand in many places. The negative aspect of it, however, is that when we are putting higher demands on the complex, it needs to be addressed or responded to somehow. That it wouldn't be helpful to have constant response because then the mobility would be limited. So what's unique about the shoulder is that a lot of the stabilization depends on muscle contributions. And that has some influence on what I call the pathomechanics of shoulder problems, which is the next slide, Seth. Okay, so shoulder pathomechanics are soft tissue dominated. They're typically two. The main one that you will hear about is tendonitis. Okay. And not exclusively, but primarily the tendon that's involved is the supraspinatus tendon. It's a little hard to see, and I'm not in control of the cursor at the moment, but at the top of the arm bone, there's another bone just above that, which is called the acromion, and the space beneath it is called the subacromial space. So in that space is where that tendon lives. Okay, that's the one that gets damaged. Why it gets damaged is an ongoing debate. Certainly there's muscular overload and tendon overload, but one of the reasons is muscular fatigue. So if the muscles are responsible for stabilizing the joint and they're incapable of stabilizing it, you get movement, and that movement can result in a narrowing of the space and a compression of the tendon. Over time, that compression combined with the load on the tendon that normally occurs will overload it, and you'll get inflammation, potentially progressing to what we would call a rotator cuff tear. Again, with a rotator cuff tear, it's almost always the same tendon that's the vulnerable one in that space. So the sort of relevant things to think about here are, how are the bones moving, and what are the effects of work on the muscle state? Because that will affect how the bones move and then put tissues at more or less risk. The second, probably most frequent shoulder issue, other than non-specific pain, occupationally, would be osteoarthritis, which is also a movement dominated mechanism. Okay, so that's the background. Next slide, please, Seth. Okay, so it's a little bit choppy due to the online nature, but this is a digital representation of the shoulder complex, a little bit simplified in that there is no forearm or hand in this particular representation, or let's say another arm or head. But what we can see is the humerus is there, the scapula, clavicle, and a representation of the rib cage are there. So those colored lines are muscles. And I want to make a few points with this slide briefly. One is that the bones are all moving when you move your arm. So it's not limited to just thinking about where the arm is. We have to think about how the other muscles are moving relative to each other, or sorry, how the bones are moving relative to each other, because that will affect what muscles' capabilities are in different postures. So as you move up, certain muscles become less effective, other muscles become more effective, and you get this transition of which muscles are active. That can have a very important impact on how fatigue progresses. And if we're not thinking of this as a whole system, we can miss some of the progression of changes with time, et cetera. So I'll move on to the next slide, please, Seth. We have done work looking at how capacity changes with the hand location in space. Very briefly, we measured 14 muscles and 70 hand locations in 6 original directions, plus we did intermediate directions, and looked at how muscle demands change. And it's fairly predictable if you consider a work envelope on the sort of semi-spherical shell around the sort of the colorized one on the left. Around the mannequin is a kind of a amalgamation of all of the muscles in terms of where you would have lower demands at this distance from a worker or a person. And what you can see is in the preferred working envelope, it's basically blue, which is better, and it gets red as you get away from that. So clearly the higher you go in terms of what we're talking about today, the redder it gets. And that means we have higher muscular demands proportionally. At the bottom right are some deltoid examples where you can see, depending on which part of the deltoid and how far out you are, you see these same trends where there's a sweet spot in terms of where work is least demanding. And this is clearly not in the overhead zone. Okay, so next slide. We've done a lot of investigations on primary measurements of overhead work, and there is a white paper and a position paper on the CRE-MSD website talking about overhead work that's been recently updated. There are general guidelines that increase or decrease risk associated with overhead work. Exoskeletons are developing very quickly. There's a lot of research coming out all the time. So there should probably be some more bullets on this about the role of assistive devices, but they post-date when this particular work came out. But the point is that overhead work is a persistent issue, and this is an alternative perhaps to modifying those exposures. So next slide, please. This is another example of some overhead work that we did where we moved the work location and modified the force direction. And basically there are preferred force generation directions to have during overhead work. Essentially, pulling back towards the body in an overhead position is just about the worst in terms of muscle recruitment. This was for 11 muscles. And then pushing forward or pulling down are better, mainly due to weight leveraging and muscle offload. Okay, the concept here, though, is that we have measured many outcome variables over the years on that are relevant to this kind of application. So next slide. This is what we're here to talk about is, in this case, upper extremity passive exoskeletons. So the intention is to reduce shoulder demands. And I would say primarily muscular shoulder demands. And there's lots of research out there that indicates, as Seth mentioned in their own prior studies, that you do get reductions in major muscle groups. A lot of the quantifications focus on specific muscle demands, as is helpful. I hope that the sort of overview of the complexity of the system shows that a system approach is helpful. as well, in that we probably shouldn't rely on individual muscles to make large statements. Part of the reason is they may or may not relate to injury. I covered for you that the main site of injury is the supraspinatus tendon. That's a very small muscle. It's also classically difficult to measure, and also fatigue susceptible. So there could be potential complications if it's not being monitored. Many of not all, but a lot of the existing knowledge is based on shorter exposures. And the sort of soft tissue damage we see in the shoulders is accumulative or cumulative exposures. And we may not be seeing how things change over time or precisely how effective it is across time. And then how does the job type affect the effectiveness or the quote appropriateness of implementation? That's still an ongoing question. There are many, many factors, and several are being addressed or ongoing being addressed, such as multitask jobs, how the individual fit would influence these, that are very valuable questions. The one that we're mostly targeting with this collaboration is looking at fatigue and more intricate muscle responses. So next slide, please. And the goals of our partnership. This is our lab. We don't normally have a vehicle suspended from the ceiling, but we get the job done, whatever we need to do. So we are attempting to assess the exoskeleton effectiveness with the guidance and for relevant questions that Toyota, our partner, has. So we are getting new metrics in terms of kinematics. Shoulder kinematics is not for the faint of heart. There are many standards, international standards, on how to report that. We are very capable of measuring it and describing it in ways that are not often done ergonomically. Also, fatigue metrics in terms of the larger shoulder complex and time over a longer period of time, some calling that advanced fatigue evaluation. We are looking at improving or investigating enhanced or additional rotator cuff characterization. The cuff is most of the story when you're thinking about shoulder pathomechanics, and then trying to help with evidence-based implementation guidance in terms of job selection, operationalization of when these exoskeletons may be more or less useful to avoid certain outcomes. So in our lab, you can see here we have our motion capture cameras set up and a person in an exoskeleton simulating a weld task. Next slide, please. Okay, and I'm not the only one that says this is important. Steve Fisher was my PhD student, but basically part of the impact of these skeletons on the shoulder or looking at muscle fatigue and kinematics will provide a more robust appraisal. And I believe this is true. This is what we need to know. Next slide. So why work together? Exactly the purpose of CRE-MSD. We're trying to connect outputs to research and give or provide resources for partners. So I'll pass it back to Seth.
Hi, Seth. I'm just going to suggest you go right to the next steps so we have time for just a couple of questions. Thanks.
Absolutely. Sorry, the next steps. Let me just, I guess I'll end off on sort of this user triangle research developer stage. So we have a number of exoskeletons that we're still evaluating here. It's not limited to just upper body, but it's primarily focused. There's some lower body ones as well as other emerging technology. There's a bunch of standards to as well. I didn't speak to ASTM F48 exoskeleton committee. It's the first well-recognized exoskeleton standard that is being worked on. We're part of that committee, as well as the North American Exoskeleton Usage Standard, as well as the Automotive Exoskeleton Partnership with BMW, Nissan, Honda, Ford, and even Tesla and Boeing has joined. And then other research that's out there, as we stated, we've been working a lot with Iowa State. NIOSH is developing a more longitudinal effect of exoskeletons, shoulder exoskeletons, and then our work with Waterloo. Thank you.
Thank you so much, Seth and Clark. We really appreciate your presentation, and we will open it up for questions and ask people to type their questions into the chat box. And maybe you could just kick off this question and answer session by just identifying, how do you decide, is it related to injury or is it related to trend across your sector? What exoskeleton needs to be built? Seth?
Sorry, can you repeat that?
So the question is, to decide on an exoskeleton, the development of a new exoskeleton, is this related?
Okay, yeah.
Yeah. How do you do that? Is it related to injuries? Is it related to trends in your industry? What metrics dictate, if any, how you go forward with what?
So far, we haven't put through any sort of new exoskeleton based on our needs, either through an injury or risk point of view. It's been mostly matching what's out there to our current needs now. Through the automotive working group, we have made sort of a needs analysis of the areas that a developer could get their hands on, and we have been involved with some startups, but so far it's not quite clear cut yet on how we take this information and put it out there for others to take hold. So far, it's been very much existing tools trying to match to our existing processes.
Okay, thank you for that. For the longer durations in welding, were there any issues with employees' hands going numb?
Blood flow loss is one that we're closely monitoring, as I'm sure this someone who was asking that question is aware that overhead work for a long period of time could result in that, especially if they're holding something. So for the most part, even though they are long durations above head, they have capabilities of dropping their arms at any point. So they can provide those micro breaks embedded into the process. They're not there's no moving carrier system in that point. So they're very capable of switching up the task. So far, we haven't come across of numb or tingliness or white hands or any of that sort of thing yet.
Okay, thank you. Just wondering if you've had any issues to overcome on trust of the technology on the part of the employees, as well as any unions involved.
Yeah, trust is a huge one. If we can't win our team members over to rely on the use based on the research, which is basically the biggest point for us, is to make sure we are very much providing our source or reasoning why we're going with this. It's been a part of the plans since day one. So yeah, it's been a big part of it. As far as union goes, we are a non-unionized organization. We have a strong internal responsibility system here, and in regards to engaging with our team members from a safety point of view, we have a joint health and safety committee that has reviewed and bought off on this activity. The worker representatives is important to us and very much embedded into what we do.
Thank you so much. I'm not sure if either of you can answer this, but I'll send it out there anyway. Any experiences of using exoskeletons in hospitals for patient handling?
I'll come in quickly just to say that we
Okay,
have done
thank you.
this is Clark, patient handling research, but not with exoskeletons at this point. I don't know if Seth is aware of anything in that.
No, I'm afraid I'm not.
All right, and I think we do have some other researchers involved in looking at that, and if something comes up, we will share that with our audience. What is the range in cost for various exoskeletons?
It seems to be sort of the 3 to 6K mark per unit. That's generally speaking, that's been the low and high costs of them that we've seen so far.
Okay. And with respect to the straps, are there male and female models, or do you have only males in the roles using these exoskeletons? One picture showed the straps, including across the chest, and the one picture would not be comfortable for females.
Yeah, that has been part of the discussion. The strap across the chest is an optional strap, completely for preference. Think of it like a backpack. Not everybody needs to use that type of strap. But so far it's been very much primarily males, only because that's our demographic of work in these areas, not by any sort of great reason for it. But it has come up, and we do have female users. If they don't have a strap across the chest, then it seems to work just as well. Some exoskeletons are more geared towards males than others, but yeah, it's been there.
Great. Thank you for that, Seth. And this will be the last question. I will encourage people, if you have questions that don't get answered or questions occur to you, you have our presenters' information on this final slide, and they're happy to respond through email to any questions you have. Our final question is, have the exoskeletons affected productivity positively or negatively?
Yeah, it's been dependent on each trial that we've done. In some cases, very positively based on the weld processes. They've all stated that they cannot perform their job without it. So in that case, it very much, there's a huge reliance on this technology to being there to actively use, versus the interferences that we're seeing in assembly through that dynamic work aspect. That's the negative side of things that we're trying to figure out. So I can't really say overall which one kind of outweighs the other. We're still going to evaluate both.
Thank you so much. I'd like to thank all of you for joining us today and encourage you to join us on June 25th for our next free webinar with Dr. Nick Ladelfa on neuromechanical response to repetitive workloads relative to current upper extremity ergonomic thresholds. Thank you so much, Seth and Clark. Just fabulous information, and we look forward to hearing more down the road about the use of exoskeletons and seeing our participants at our upcoming webinars. Have a great rest of the day, everyone.